All right, ladies and gentlemen, this is going to be your note set about how to do electron dot structures and electron configurations. So far we've looked at the periodic table in terms of atoms, right? And that makes sense, this is chemistry. But now we need to really focus hard on electrons. So let's talk about electron dot structures first, because that's the easiest thing to do. An electron dot structure is going to tell you about the valence or the outer electrons in any given atom, right? So up on the top here in this yellow color, I've put the information for how many outermost electrons everything in that vertical column has, or that group. So everything in group 1 is going to have 1 valence electron, everything in group 2 is going to have 2 valence electrons, so on and so forth. In terms of how to draw the electron dot structure, it's actually very simple. Let's say we're going to do the element, let's say beryllium, which is right here on the periodic table. That's in group 2, so I know it's going to have 2 outermost electrons. So all I need to do is put the symbol for beryllium and then draw 2 dots around it. And that's the electron dot structure for beryllium. But let's say, for example, I wanted to do a different one. Let's say I wanted to do, I don't know, fluorine, which is over here on the periodic table. That is going to have 7 valence electrons, so I'm going to end up drawing 7 dots around it over here. But once again, I'm going to put the symbol for fluorine, and I'm going to draw 7 dots. Now there is a pattern to this. I like to imagine that there's a box around that element, and I have to put a dot on each side of the box before I can go back and pair up any of those dots. So since fluorine has 7, I'm going to do 1, 2, 3, 4, and then start pairing up for 5, 6, and 7. All right? Let's do one more example. Let's say we wanted to do, let's say silicon. And silicon is going to be in this position right here. Silicon is going to have 4 valence electrons. So if I wanted to do that one, I would draw the symbol for silicon, and I would do 1, 2, 3, 4. Oops, that looks like an E. 4. And I'm not pairing any of them up because I have 1 dot on each side of that invisible box before I go back and start pairing anything. All right, so electron dot structures are very easy. Electron configuration, on the other hand, is a code, and that code tells you where electrons are at any given time. Now there's 3 main pieces to all of this code. We have the row number, which comes first, and that's going to be the big number in front of that code. And it just tells you what row you're in on the periodic table. So if you look at how I've labeled all of this, row 1, 2, 3, 4, 5, 6, and 7, that's the big number. The next piece of the code is a letter, and that letter tells you what type of orbital space you are in. Now, an orbital space is just any space that can contain an electron, right? And that orbital space can look very different. So we can have 4 options for letters. S, over here, those are spherical orbitals. They are rounded, and they only contain 1 orbital space per row, right? So if we're going to draw out an orbital diagram, you would specifically want to draw 1 line for that. P orbital spaces over here are kind of weird. They're a little dumbbell shaped, and per row, there are 3 of those dumbbell-shaped p orbital spaces, so you would draw 3 lines in an orbital diagram. D orbital spaces are cloverleaf-shaped, and we would draw 5 lines because there are 5 of those orbital spaces per row. And then finally, F orbitals are just odd-shaped. There's a lot of different options, this one in here being the most common, but there's 7 of those orbital spaces per row, and so you would draw 7 lines in an orbital diagram. So let me give you an example of what that code might in fact look like. Remember, we have a big letter, or big number, a letter, and a little number that tells you how many boxes over in that row you are. So let's say that piece of my code was 3D4. All right, that's going to correspond to a space on the periodic table. So you find the row that says 3D and you count 1, 2, 3, 4 boxes over, and that's the space you're in. Let's say that piece of my code was 5P5. Well, you find the area over here that says 5P and you count over 1, 2, 3, 4, 5. And that is your orbital space that you're occupying. So, again, this code is very easy to read, but you are going to have to generate it. So, let's talk about a practice problem down here. So, lithium, for example. Lithium, if you want to do the electron dot diagram for it, again, that's very easy. Lithium is going to occupy this space right here on the periodic table. So we know that that's going to have one valence electron. So if I do the electron dot structure for it, it would look like that. That's super easy. In terms of the electron configuration, that one's a little bit more complicated, but not super hard. We always want to start up here at the space that hydrogen is, and we want to stop when we hit our element, okay? And again, lithium is occupying that space right there on the periodic table, okay? So I'm going to describe every single electron that lithium has, and as we know, on the periodic table, lithium has a total of 3 electrons. So we're going to have a couple pieces to this code, all right? Now, for our full electron configuration, we always want to put the symbol, and then we put a colon. If we're going to start up here in the first row, we're going to describe everything in that row. So we're going to take my piece of my code. I'm going to put a big number 1 because I'm starting in row 1. I'm going to say the letter S because the only type of box I see in row 1 is S, and there are 2 total S boxes in row 1. So I'm going to put a little exponent of a 2. Now, I'm going to hop down to the second row, row 2. Lithium's in that row. So I'm going to put a big 2, so I'm in row 2. We're still in an S box, and lithium is the very first box in that row. So 2S1 would be the rest of that code. All right? Easy enough. But let's do another example. Instead of lithium this time, what if I did carbon? I'm going to cross that out and put carbon. Carbon is going to occupy this spot on the periodic table. I'm just going to take a second to erase some of the arrows and stuff that I had on there before. All right. So carbon, once again, is going to occupy this space right here. So let's do its dot diagram first. We would put its big chemical symbol, and it is in group 14, so it's going to have 4 valence electrons around it. 1, 2, 3, 4. Super easy. All right. Now, we're going to do its electron configuration. Once again, we're going to put the chemical symbol. We're going to put a little colon. Now, we're still starting all the way up here at hydrogen. So we're still going to describe row 1 first. Row 1, S box, there's 2 of them. Great. Now we're going to move on to row 2. We're in row 2. We're again looking at an S box first, and there's 2 of those in row 2. So now we've done that, and we're going to move on here. We're still in row 2, but this time we're in a P box, and carbon is the second box over in that row, and we stop when we hit carbon. Okay? So this is, again, not super difficult, but I just want you to get the hang of reading this periodic table like that. All right. I'm going to take a second to erase some of those things, and we're going to do one more example of a full electron configuration, but this one's going to be a little long. This time we're going to do astatine, which is AT, and that's going to occupy this spot right there on the periodic table. This one's going to be a little bit long for the full electron configuration, but bear with me. All right. Astatine, for its dot diagram, that is in group 17, so we're going to draw 7 total dots. 1, 2, 3, 4, 5, 6, 7. Easy enough dot diagram. And now for the electron configuration, which is going to be just a little bit long. All right. So we're going to go ahead and put its chemical symbol here. I'm going to do this a little bit spaced out so we have room to do the orbital diagram afterward. Now, once again, we're going to start always up here at hydrogen. We have our first row, S block, 2 total boxes. All right, now I'm done with row 1. Then I have my second row. First thing I see is S. There's 2 of them. Then I'm going to do, 2p, right? Because I have to move all the way across and do 2p. And there's 6 of those boxes. So we put a 6. Then we're going to go ahead and move down to row 3. Row 3, S, 2 of them. I'm going to take a second real quick and then create some more space for us. I'm just going to scratch that up for a second, deal with that later. All right, now we're going to move across to the 3p row. 3p6 is next. Then we have 4s2. Then we have 3d10. Then we have 4p6. Then we have 5s2. I'm going to just scratch out that orbital diagram so that we have enough room. All right. Next we have 4d10. 5p6, then we have 6s2. Now here's where it gets fun. There's a little green sliver there. What that means is when we're reading the periodic table, that green bit comes next. So right after 6s2, we're actually going to do, ooh, that was a terrible line. We're going to do 4f14. Then we come back and we do 5d10. And then we can finish out with our 6p5. So that was a lot. That was a lot of electron configuration. However, there is a way to do this a little bit faster. There is. It's called noble gas configuration. So as we know, the noble gas row is group 18. So I'm going to put a little star by it up there. And the noble gas row, or group, I should say, is very, very stable. And we can use that as a standard, which is super helpful for this. So if we don't want to start all the way at hydrogen, which I don't know about you, but that was a very, very painful configuration to do because it was so long, you can actually move your starting point from here to one of the noble gases. So in this case, if I wanted to do the noble gas configuration of astatine, which I'm going to do up here since I have my full configuration down there, I can actually move to the noble gas right before astatine, right? Which, if we look at our periodic table, that is going to be the element xenon. So again, instead of starting at hydrogen, I can just start at xenon and tell my audience that I'm starting at xenon instead. I'm going to put it in brackets, and then all I have to do is the configuration for the row that's left over in astatine, right? So if I start at xenon, my next one would be 6s2, and then I would do my 4f14, and then I can finish out with 6p5. So noble gas configuration is actually a lot shorter and a lot friendlier. But unfortunately, we need the full configuration sometimes. And the reason we need that is because sometimes we need to do an orbital diagram. So let's talk about an orbital diagram. Orbital diagrams are essentially an expansion of the full configuration. So all this information here and here and here about how many lines to draw, this is when that becomes relevant. So in our full configuration, every time you see the letter S, you're going to draw a line underneath it. So I'm going to go ahead and do that for every single letter S that I see. Every time that you see the letter P, you're going to draw 3 lines. And then every time you see a letter D, you're going to draw 5 lines. And then finally, every time you see a letter F, you're going to draw 7 lines, and that's going to look a little smushy, but that's okay. All right, now once you've done that, you've set up your configuration so that you can do an orbital diagram. So I'm going to do this in kind of a bright color so you can see it really easily. Now, the next thing you pay attention to after you draw your lines is the exponent number, because that's going to tell you how many arrows to draw on that line. So this S1 has an exponent of 2. So we're going to draw 2 arrows, and they're these little half arrows. Why do you use half arrows? Because somebody decided at some point that you should, but if 2 arrows are on the same line, they got to be spinning the opposite direction. So every time you see an S with a 2, we put 2 arrows. All right, now every time you see the letter P, we're going to put that amount of arrows on the line. 1, 2, 3, 4, 5, 6. Now I want to talk for a second about how I just filled that out. You will notice that I put an up arrow on every single line before I went back and paired them up and put my down arrows. There is a reason for that. Electrons do not like to pair up unless they have to, because electrons have negative charge, right? And they like to repel each other. But if they are spinning in an opposite direction, which is what this opposite direction arrow thing means, then they can pair up. And so it's important that when you're doing an orbital diagram, you fill in all of your up arrows on every line before you go back and start pairing them up. All right, this one. I'm going to leave this one alone till the end because it's unfinished. All right, now for D's, we got 10 electrons and 5 lines to distribute. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's another D. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Here's another D. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Last but not least, we've got F, 14 arrows, 7 lines to distribute them on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, now we're almost done. We're almost done. I have this last unfilled orbital to complete. All right, now once again, we have 3 lines and 5 electrons, so this one's going to be unfinished. We're going to do 1, 2, 3, 4, 5. All right, now I just want to talk about something really quickly. If that last bit of the configuration had been 6p3, that is when filling out your arrows like that becomes important, right? Because 6p3 should look like this. However, if you didn't know about the arrow thing, you wouldn't draw it like that, like automatically, right? Because some people draw 6p3 like this, and that is incorrect. It is most correct to put a single arrow on all of 3 of those lines before you go back and pair them up. So that's why I draw it like that, because sometimes you will draw it incorrectly if you don't know about that rule. All right, so let's just go ahead and mark that as wrong, and we'll mark this one as correct. Okay. Now, that is a full orbital diagram. The good news for you is that the orbital diagrams, the arrow bit and the line drawing part of that, that's extra credit. The only thing that you absolutely need to know how to do is the full electron configuration, the noble gas configuration, and of course, the dot diagram. But again, the arrow stuff, that's extra credit. If you're having trouble with any of this, please let me know.